Hey, this is Mrs. Weethy. Welcome to our next unit, Unit 4, in the periodic table and the periodic law. So get your stuff out, get ready to go, because here we go. Okay, back in the late 1700s, Antoine Lavoisier, who was a chemist, he was doing a lot of research with gases at the time, and one interesting thing about him is that his wife Marie was his assistant. He was also a tax collector in France, and during the French Revolution, they were gathering all the political people, which tax collectors were included, and they beheaded them. And that was the fate of Antoine Lavoisier. But his wife, Marie, she kept his research going, and if they would have found out, which was against the law for a woman to conduct scientific experiments, she would have been beheaded as well. Well, he compiled a list of known elements. There were 33 of them at the time, and he organized them into four basic categories: the gases, the metals, the non-metals, and the earths. And the earths are those elements that you could actually extract out of the earth. Now, the number of elements continued to grow and grow in the 1800s due to a variety of things. One was the advent of electricity, the development of the spectrometer, and we used a student spectroscope in class to see the spectral lines and see how that acts as a fingerprint for elements. And then, of course, the Industrial Revolution in the mid 1800s led to many new chemistry based industries, which led to the discovery of a lot of the new elements. John Newlands in 1864 organized the elements, 70 of them at the time, in increasing atomic mass order. He noticed that the properties of the elements repeated every eighth element, and he called this repeating pattern periodic. Because the properties of the elements repeated every eighth element, this repeating pattern was known as the law of octaves. Now, in 1869, Dmitry Mendeleev, who was a Russian chemist, was hired at a university, and he was writing a chemistry textbook, and he decided that he wanted to publish a classification or organization of those elements that were known. And he did this and published the very first periodic table. However, that periodic table was very controversial. Like Newlands, he noticed a repeating pattern in the properties of the elements. He did the same thing and arranged those elements by atomic mass, but he also placed elements with similar chemical and physical properties into the same groups. Now, this is what his periodic table looked like. Now, notice, if you take a look at this group that we have right here, this would be group 1. His groups were actually horizontal, where ours are vertical. But take a look at the outline, these two that are outlined in red, and there's question marks there. One of the controversial things that he did is he left gaps in his periodic table, but he said that those gaps represent elements that were not yet discovered. Well, scientists didn't like that. They wanted an answer for everything, but he couldn't give them that answer. He just said they simply were not discovered yet. The other problem with his periodic table was right here. You have tellurium with an atomic mass of 128, iodine with an atomic mass of 127. He placed tellurium before iodine, even though tellurium's mass was higher than iodine. And the scientists, how can you justify that? And what he said is that tellurium's chemical and physical properties were similar to selenium and sulfur and oxygen, and iodine's properties were more closer to bromine, chlorine, and fluorine. So to him it made sense to just flip-flop them. But without any proof, the scientific community really didn't buy it. So these were the two problems. Some of the elements were out of atomic mass order because they were more similar to elements within the group that Dmitry placed them in. And second, there were those gaps, and those gaps represented undiscovered elements. Now, the one thing about the arrangement of Mendeleev's periodic table is that those repeating patterns were so specific that he could accurately predict the properties of those undiscovered elements. Let's take a look at one. This element he called ecosilicon. Eka means after, so this is the element comes after silicon. These are the properties that he predicted. He said that the atomic weight mass of that element would be 72. When that element was discovered, it was germanium, and the actual atomic mass was 72.59. He predicted the density to be 5.5 grams per centimeter cubed. The actual density is 5.35. And as you go down these predicted properties, you can see that they're very close, if not exactly the same as the actual properties. Look at the form of an oxide, how many oxygens it's going to form a bond with. He predicted that that element would combine with 2 oxygens. In fact, germanium does combine with 2 oxygens. He predicted that that element would combine with 4 chlorines, and in fact, germanium does. So those predicted properties very, very close to the actual properties. Now, in 1913, almost 40 years after the fact, Henry Moseley rearranged the periodic table, but now he did it based on atomic number, increasing atomic number, the number of protons. And why was he able to do this? Because of the discovery of the nucleus and the protons that Ernest Rutherford did with the gold foil experiment. Moseley proposed the periodic law, which states that there is a periodic repetition of chemical and physical properties of the elements when arranged by increasing atomic number. And very simply what that means is, once you get to group 18 and you go down to the next energy level and you start with group 1, you're starting all over again with the same or very similar chemical and physical properties, and those are going to continue. That pattern's going to continue until you get to group 18 and go back to group 1. Okay, so the organization of the periodic table, the periods are the horizontal rows. We know that there are 7 of them, equal to the number of energy levels, and the groups are the vertical columns. The vertical column, or the elements that are within the same group, have the same number of valence electrons. Thus, they have very similar chemical properties. The reactivity of the elements is determined by the number of valence electrons. The stability of the elements is all the elements when interacting in a chemical reaction want to achieve a complete octet. And why is this? Well, let's take a look at that. The closer to a complete octet an element is before forming a bond and while interacting, then the more reactive an element is. Well, we know that sodium has 1 valence electron. Okay, has that 1 valence electron. So if we actually write the electron configuration, we have 1s2, 2s2, 2p6, 3s1. So if we take that 3s1 and we remove it, then we get a noble gas configuration. So that makes sodium very, very reactive. Fluorine, on the other hand, its configuration is 1s2, 2s2, 2p5. So it only needs 1 more electron. And if we add in that 1 more electron, now we have a complete octet, and that makes fluorine very, very reactive. Now we do have an exception, and those are those elements in period 1. They only need 2 electrons to be chemically stable, and let's take a look at that. If we take a look at hydrogen, hydrogen has only 1 electron, and that 1 electron is going to go in the 1s. So all it needs is just one more electron to make a complete energy level. And the same thing with helium. Helium has two electrons. And when you put those two electrons into the 1s, now you have a completely filled first energy level. And we call this, when you have only two electrons to complete an energy level, is a stable duet. Okay, that completes lesson 1 in unit 4. Until lesson 2, goodbye for now.